welcome to the session. So in this particular video, we will talk about the very first introductory session of dynamic programming. We will try to see that what is the meaning of dynamic programming, at what point of time we should go for this dynamic programming approach. I know that this particular module is pretty much important in terms of whenever you are trying for a good product-based companies like Google and Amazon, because they can ask you the questions related to this module. But the major prerequisite to understand the complete in-depth knowledge of this module is the recursion. So if someone is not aware about the recursion that we have covered up in our very first module of divide and conquer, then you might face difficulty in understanding of this module. That's why at that point of time itself, when I was talking about the recursion, I told you that don't directly jump towards the advanced concepts of DSA. First of all, try to get expertise in the basic things, for example, recursion. So recursion is pretty much important whenever we are talking about divide and conquer. And now recursion again plays a very important role when I am talking about a dynamic programming. So if someone is not having a good idea and good command over recursion, I would suggest to that person that firstly go to that session itself, try to get expertise over there, practice a lot about the recursion problems, and then come towards this particular session of dynamic programming. So let's get started with the concept of DP. So whenever we are talking about something that we called as dynamic programming, a most awaited module, right? So this is again a way to solve any kind of, I would say, optimization problems. Optimization problems. Now I hope that everyone knows what is the meaning of optimization problems. The simple meaning is that whenever I want to find out some minima or something called as maxima in a given problem, I will go for the dynamic programming or the greedy approaches. Both of the tools are utilized to solve the optimization problems. But the question is, at what point of time, which particular tool is important? Secondly, what is the difference between dynamic programming versus the divide and conquer approach that we already have discussed, right? Or at what point of time we should get an intuition that, okay, this problem we can solve with the dynamic programming. So there is something which we called as the concept of overlapping subproblems. Overlapping subproblems. So what this concept says, please try to understand this concept. For example, I would like to take one example of a Fibonacci series. What is Fibonacci series, by the way? It says that the starting element is 1 and 1, and from the third element, it will be the summation of the previous twos. So it will be 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, and it will be so on. So what I am saying is that the Fibonacci series says that when the value of n is equals to 1 or when the value of n is equals to 2, the result is something which is equals to 1 itself, right? Otherwise, in other scenarios, I can say that the result is something which is the summation of the previous two numbers, which is n minus 1 plus the value of n minus 2. Can I say? Where you can say that fib of n is something which is the number that we have, which we want to find out. For example, if I am entering the value of n as suppose 4, so it will return me the solution as the output should be equals to something which is equals to 3. Because 1 is 1, 2 is 1, 3 is 2, 4 is 3. This is the output returned by the series. Can I say? Here if you will observe, if suppose I want to find out the output of n is equals to 5. So the very first thing that I hope everyone has already been observed, that This is the function name, and I am calling the same function again inside the method definition. And finally, what I am trying to do here is that I am trying to simply return the value of the result, right? So somewhere I am saying that here recursion is coming into picture. And as I told you in the starting of the session itself, recursion will always come whenever we are solving a DP kind of a problem. Now, what will happen? Suppose I will try to solve for a value of fib of 5. As the value of 5 is greater than 2, so it will go in otherwise situation and it will try to find out the value of fib of 4 and the value of fib of 3, can I say? Further, at the time of fib of 4, again it will try to split into two parts and it will try to find out the value of fib of 3 and fib of 2. Can I say? Because what we are doing is that when it will go to otherwise situation, it will go to otherwise situation when the value of n is greater than 2, right? So here if you will observe, the value of n is greater than 2 itself. So here if you will see again, it is 3 which is greater than 2. So what will happen? It will try to calculate the value of fib of 2 and the value of fib of 1. Now we know that the value of fib of 1 is 1, value of fib of 2 is also 1. Similarly, here also the same split will happen, fib of 2 and fib of 1. Can I say? Now, here one thing which you need to observe is that we are solving. So here how the function call will happen? Function call will firstly go here, then C2 will be called, then C3 will be called, then C4 will be called and it will return the solution as 1. Then C5 will be called, it will return the solution as 1. Then C3 will be called and it will return the solution as 1 plus 1 which is equals to 2. So it will return, I would say 1, right? Because the value of n is 2. It will return 1, and when the function call will go back to C3, it will return the value as 2, the summation of the previous 2's. Now when it will go back to C2, this C6 will be called and it will return the value as 1. 2 plus 1 is 3 which will be called. Now again the function call will go back to C7. C7 will call C8. C8 will again return the value as 1. Then C9 will be called. It will again return the value as 1. So this is something which I am creating as a recursive tree, and I am not going in that much depth because I already have explained this concept of recursive tree in a very much detail in the divide and conquer module. Here I am just showing to you that what is happening. Then C7 will again return the value as 2. 3 plus 2 is something which we called as 5. So the final answer 5 will be returned. Is everyone agrees with me? So here also if you will observe, for 1, 1 is returned, for 2, 1 is returned, for 3, 2 is returned, for 4, 3 is returned, for 5, yes, 5 is returned. So we are getting the correct output, right? Using the recursion approach. Now, here if you will observe, I solved initially the value of fib 3. And here I am again solving the value of fib 3 again, right? I am utilizing the same resource several number of times. And this problem is something which we called as overlapping subproblems. Overlapping subproblems. This problem is something which I will call it as overlapping subproblems. And our objective is to resolve these subproblems, right? Now the question is how we can resolve this. If suppose I will try to store the result of fib of 3 as 2 already in some sort of array or something like that, right? So if in an array I will be already able to store the result, right? Then what will happen? Before doing the calculation, I will just keep a check that if the value of fib of 3 is already present in that array or not. In this way, I will be able to utilize my resource efficiently. In this way, I will be able to reduce the time required to do the computations internally, right? This is something where I am storing the result of the recursive subtree in some sort of an array is something called as memoization approach in the dynamic programming. Memoization approach in the dynamic programming. So here what we are trying to do is that we are trying to solve the problem using recursion only. Now what we are trying to do is that inside that we are trying to store the results side by side. The same thing we are trying to do here, the similar thing, but whenever we are trying to see a situation of overlapping subproblem, we will try to store the results so that my code will not do the computation again and again. And at that point of time, this approach is something which we called as memoization, not memorization. Memoization, right? It is also known as top-down approach because we are starting from the topmost level and we are going at down where I will reach to a base case condition. This approach is also known as top-down approach, right? So in the recursion, we are just trying to store the results which we are not doing in the divide and conquer part. Now, here one question comes. If you will remember the example of a merge sort, which we have discussed in our previous sessions. In the merge sort, there was no problem of overlapping subproblems. If you will try to go there and again recheck the recursive tree that I have created for the merge sort, there is no as such overlapping subproblem. That's why we will be easily able to solve that problem using a divide and conquer approach. And even there is no need to apply any other approach there as well, right? Because there is not a situation of overlapping subproblem. Wherever there is a problem of overlapping subproblem, what is the meaning of that? That similar type of function calls are executing again and again. And here you can clearly see that we are trying to solve for a very small number where the value of n is 5 as of now. If suppose when the value of n is greater than 5, at that point of time this problem is really big because it will try to take a lot of time. Suppose you can at your home try to create for the value of n as 20. You will observe yourself that a lot of time we are wasting in terms of using and calculating the same value again and again. So at that point of time, researchers came across this thought that why not to store the result within some array. And before doing any sort of calculation, we will just give a check that whether that result is already present in that array or not. If it is present, we can directly take that. If it is not present, we can directly calculate that, right? This is something we called as memoization. There is another thing which we called as tabulation, which is called as the bottom-up approach, where what we will try to do is we will try to create one table, and inside that table we will try to store the results from the very bottom, right? What we can do, we can simply try to take one table, right? Inside that what we can do, so in this case we are not using any recursion. I will show you the code part as well for the Fibonacci series, with the help of which you will be clearly able to understand. So in tabulation approach in DP, we are not using any sort of recursion there. So here what we are trying to do, we are trying to directly apply the values. For example, for the value of fib of 1, it will be directly 1. You are initializing it as 1 only. For the third part, you are directly giving the last two numbers, you will get the summation. So it will be 2. For the fourth calculation, again, you are directly giving the numbers, it will be 3. For the fifth, it will be 5. For the sixth, it will be 8, and so on. So here, you are directly providing the numbers inside the table. I will show you. So in this particular case, there is no recursion which I am using, right? So you can solve the problem either by using the recursion or by using the tabulation. Now you can ask me one question that, okay, how it is effective in terms of time complexity? Can you talk about that? Now if I will talk about the time complexity of the same. So what is the recurrence relation, by the way, for this particular code? If suppose this is t of n, so can I say that when I am having a small problem, means when the value of n is less than 2, less than equal to 2, it will be constant only, right? But when the value is big, means the value is n is greater than 2, at that point of time it is nothing but is equals to t of n minus 1 plus the value of t of n minus 2, right? So can I say that the recurrence relation of this Fibonacci series will be something which is equals to t of n minus 1 plus t of n minus 2? Can we say? If I will try to solve this, because here I am having more than 2 recursive terms, I can solve this using a recursive tree approach, right? Recursive tree approach. How we can solve that? So this is something which we are getting as a recurrence relation. Recurrence relation. So here, if you will observe what we are trying to do, n is split into 2 parts, n minus 1 and n minus 2. And the cost required for this computation is c only, right? Now again n minus 1 will get further split into 2 parts. It will be n minus 2 and n minus 3. The cost required will be c and c, so it will become 2c. Again here it will be getting split into 2 parts, n minus 3 and n minus 4, and individual cost required for the computation will be constant c. So it will be something which is equals to 2 to the power 2 into c. Now those who are aware about how recursive tree approach will work, they only will be able to understand what I am writing here, right? Now the question is, how many number of levels do we repeat this task? So on the left side, we are doing a subtraction by 2 by 1, and on the right side, we are doing a subtraction by 2, right? So n minus, here we are trying to do the subtraction by 1. So it will be n minus k equals to 1, and here it will be on the right side, it will be n minus, because we are doing a subtraction by 2 times. So it will be n minus 2k, which is equals to 1. So for the left side, this is what we are trying to do, right? And on the right side, this is what we are trying to do here. So here if I will talk about the value of k, so the value of k will come out to be n minus 1. Similarly, here if I will talk about the value of k will come out to be n minus 1 divided by 2. So what we are doing, in the left side, I can say that the number of levels that we are traversing here will be k. Can I say? Will be k, which is equals to n, because n minus 1 I am taking constant apart. So on the left side we will be having n levels, and on the right side we will be having, in a way, n by 2 number of levels. So which is having a higher value? N. So what I am saying is that with what we will do, we will try to keep on adding until the value of k, because at each and every level the cost is different. So what I can do, I can take c as common. I can say 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus until so on, until we reach to the last level, which is k. And the k is equals to n. So what we can do, we can say 2 to the power 0, 2 to the power 1, 2 until the value of 2 to the power n. Because the value of k is equals to n, here we are talking about the maximum value. What is the maximum number of levels we can go? This is something which I can say is a GP series. Can we say it is a GP series? Where the common ratio r is something which is equals to 2. So what is the sum of a GP series? It is nothing but when the value of r is greater than 1. At that point of time, it will be a into r to the power n minus 1 divided by r minus 1. So I can say value of a is 2 to the power 0, which is equals to 1 itself, into r is 2 to the power n minus 1, divided by 2 minus 1 is 1 itself. So can I say that the time complexity required to do the above task with recursion is exponential? So this is the recurrence relation when we are doing the code with the recursion, right? The time complexity is something which we are getting as exponential here. Exponential time complexity. And if you remember the time complexity class in the very starting module of analysis, I told you that exponential is the very high time complexity here. So if you will observe, even with the help of the diagram of a recursive tree also, you will be able to get the intuition of the time complexity. How? Because here if you will observe, we are getting in some way CBT kind of a format, complete binary tree. Always the recursive tree which you are forming up is of the form of a CBT that we have discussed in our heap data structure. So whenever we will be having a complete binary tree, can you talk about what is the number of nodes at that point of time we have? How many number of levels do we have? Right? The value of k, if you remember in that session we have discussed, will be equals to 2 to the power n minus 1. In a CBT, the number of levels will be equal to 2 to the power n minus 1, where n is the number of nodes that we have in a recursive tree. The number of nodes in a recursive tree is something which is equals to function calls. So it means that we will be having 2 to the power n function calls. Can I say? 2 to the power n function calls are there. And this is what we called as the time complexity, which is equals to big O of 2 to the power n. So you don't even need to solve in a very much depth using recursive tree approach. Anyhow, I showed you both of the approaches. I have shown you how it is getting exponential time complexity by seeing the recursive tree approach method or by seeing itself the recursive tree also. We know that recursive tree always form a CBT kind of a structure. And we know the relationship between the number of levels and the number of nodes in case of a CBT. Because we have discussed in our heap data structure that there is a relationship between the number of levels and the number of nodes. The value of k is equals to 2 to the power n minus 1 in case of a complete binary tree, where 2 to the power n, in total we will be having those many function calls in our recursive tree, right? Because n is the number of nodes that we have, right? So here we will be able to get an idea that this is very high time complexity. Now when we are trying to do the same thing using the memoization approach, using the tabulation approach, what will happen? We will try to not solve these things again and again. So whichsoever path is repeatable, we are not solving that again. So in a way, if suppose I am having 5 function calls, so I am solving 5 number of times at max, right? We are not solving those things again and again. Suppose I want to solve fib of 5. So I will solve fib of 4, fib of 2, fib of 3, fib of 2 and fib of 1. So at max, so these values will directly be returned. For 5 function calls, we are solving only 5 things. We are not solving again and again same thing. Like in the previous case when we are doing only with the help of a recursion. Here, fib of 3 will be solved only one time. Fib of 4 will get value only one time. So what I am saying is that there is only n function calls. So the time complexity will get reduced from big O of 2 to the power n. That is from exponential time complexity. You will be able to reduce your time complexity to the linear time complexity. And that is something which is the bigger advantage of, I would say, using a dynamic programming. So now you will be having a linear time complexity instead of going towards the exponential. And that is where, so exponential we were getting when we are using the recursion, right? Linear we are getting when we are using a concept of dynamic programming. When we are either using a memoization approach or we are using a tabulation approach, dynamic programming. So that's where the advantage of dynamic programming is coming into picture. So in this way, we will be able to reduce the time complexity from exponential to the, I would say, linear. So I hope that I'm making sense to everyone. Now you will be able to appreciate that why DP is so much important, how it is coming into picture, at what point of time we should apply dynamic programming in any of the problem, wherever you will find that there is a problem of overlapping subproblem. Why in merge sort we're not applying DP? Because that kind of problem is not existing, right? So I hope that this is very much fine as the introductory part of DP, right? In the next upcoming video, we will try to solve the implementation of this Fibonacci series, which I have talked about in this particular session. And with that particular thing, you will get a much better idea that what is memoization, what is tabulation, and what will happen when we are trying to solve it without using these two approaches, right? In today's session, I just give you the gist of that. In the next upcoming module, we will talk about various applications of DP as well. For example, longest common subsequence, for example, matrix chain multiplication, and many more. So I hope that you all are excited with me to start this very fresh module of DP, and we will talk about a lot of applications so that you will be able to get an idea. If suppose you will getting some new problem in the interview, you will be able to approach towards that, right? Happy learning to all. Bye-bye everyone, and I'll see you all in my next upcoming video. Bye-bye.